Whoa, thank you. Every time I teach a course, I learn something new. Okay, so as I was mentioning, we're going to talk today about policy learning, and the idea is this. So far, when we've talked about learning policies, we really talked about doing it in an indirect way. Instead of learning pi directly, we've been talking about learning these different value functions, v and q, and then using those learned value functions to choose actions. So if you have a particular v or a particular q, that entails a policy and we follow it. But of course, we could just learn the policy directly. The policy, of course, is one way to describe it is given a state and an action, it tells us the probability that we should take that action. Another way to describe it, we've also said pi of just s gives us a probability distribution over all the possible actions. So we'll go back and forth between representing it, writing it this way, and writing it as a function of s. But the notation is going to be easier for us today if we represent it this way, write it this way. Okay, and we're going to be talking today again about model-free reinforcement learning. And if I had defined the field of reinforcement learning, I would not have used the term model-based and model-free, because model could be anything. But just remember that when we talk about it in the context of reinforcement learning, of course, what we mean is a model here is a function that goes from the current state and action to the distribution over next states. So we will be assuming we don't have that available. And sometimes another notation thing, we'll also sometimes just represent this as the conditional probability of an action given a state, same as this. Okay, so it's actually not very hard to think through. If you think, how would we represent a policy so that we could learn it? One way, of course, would be to make a neural network where the input to the network would be some representation of the current state. And the output would be probability distribution over actions that we can take. And in fact, the most common way of setting this up is to use the softmax function, which you know about, where basically if we want to represent the probability of taking action A, given state S, and a set of learned parameters theta, we'll generally refer to the parameters that define the policy, the things we're learning, by the vector theta. And so softmax is simply this equation that says we can represent, this is like a logistic function, we can represent that probability by e to some function h that we're going to end up learning, because it depends on our parameters, and then normalize that by the sum over all possible actions, summing over b to represent the possible actions of that same quantity. And so this, that denominator, of course, just assures that the probabilities over all the actions will add up to 1. Okay, so there's the softmax function. And we can then represent h, the actual function that's doing all the work, any way you like. And one simple way would be to make it a linear function of some features that you make up. Right? So for example, if you have a grid world kind of scenario, you might say, well, the state is the xy coordinate in the grid, and the features I'm going to use could be those coordinates plus I could also talk about the direction that the action is taking. Those can be features. But whatever you think is appropriate, this is the engineering part. This is where the art, not the science, of reinforcement learning comes in. If you make up a feature vector that's computed from the state in action, then we can say, well, H is just a linear weighted sum of those features, and we could learn the parameters for that linear function. Alternatively, you can go as complicated as you like. H could be instead a convolutional neural network that's looking at the pixels in the camera that the robot is holding. And the output of that trained neural network could be our H function. And in fact, the common way of training neural networks, if we want them to output probability distributions, is in fact to train them with as many layers as we need, and then make the final layer simply a softmax layer, which is applying this fixed function to the output of all those of the n-1th layer, which we can think of as just computing these features. Computing some features and getting the H function. Okay, so again, this is kind of where the art comes in, and in your projects, you'll get a chance to experience that art directly. So just to take a kind of quick look at the big picture, we've talked about learning value functions. Now we're talking about instead learning policies directly. In fact, there's a class of algorithms called actor-critic, which we've mentioned briefly already, where we have the agent learn both a value function and a policy function, and use that value function to bootstrap the learning of the policy function. And the policy in the case of value functions is implicit. Here we're going to be learning things, the policy directly, and as I mentioned, actor-critic is a combination, a blend of those two. Now, why would you want to do such a thing? One of the, it's really like the first thing you should think of if you're thinking about reinforcement learning. We want to learn a policy, so let's learn a policy. Learning value functions, we justify doing that instead because, as you now know, it's actually sometimes easier to learn the value function. But the advantage of learning a policy directly is it will turn out we can make pretty good guarantees about convergence properties just based on if we train the policy with the right sample of data. We'll say more about that as we go. And also, if you think about it, if I represent my policy as a neural net that goes from a state to an action, then I could, since neural nets have continuous outputs, I could also think about continuous actions. Right? So instead of saying, is it action 1 through n, which action should I do? I could say, well, there's a continuous action. I'm a self-driving car. What's the exact angle that I should steer here? And there are an infinite number of angles, so it's nice to be able to represent continuous actions. And, in fact, work on continuous representations of state, too, like pixel intensities. Also, we can learn stochastic policies. The way we've been talking about using value functions is not very stochastic. Well, we talked about epsilon using a parameter epsilon to define what's the probability that we'll take a random action versus the action recommended by the policy. But in fact, there are cases where we want to learn non-deterministic policies that aren't just choosing random actions, but doing something more sophisticated, and we can do that directly. The main disadvantage is that because we're going to end up using our old friend gradient ascent search to learn the policy, then we have the normal pitfalls of gradient descent search, which is that we might end up learning finding a local optimum policy. Okay, so let's look at one example. By the way, a lot of this lecture I looked at a number of different ways that other people had presented this material, and I decided, as far as I'm concerned, chapter 13 of our textbook of the Bartow and Sutton book is by far the most clear presentation. So I strongly, 3 times recommend that you read chapter 13. And in fact, many of my pictures in this lecture come from chapter 13. So here's an example of a simple world and reinforcement learning problem that illustrates why we might want to be able to learn stochastic policies. So in this case, it's a grid world with an absorbing goal state. We have a reward of -1 every time we take an action until we get to the goal state, then it's over. So basically, we want to minimize the number of steps to get to the goal state. There are 2 available actions. The actions, I could call them L and R. And in these 2 states, the L action makes you learn step left, and the R action makes you step right. But in this other state, the L action makes you actually go right, and the R action makes you actually go left. Okay, so it's a state-dependent action outcome, like most action outcomes are. And also there's a paucity of sensory data here, so that the agent can actually not distinguish this state from this state. They look the same. And so in this case, if you think about it, if we learn a value function for this, then we're going to end up, and then we follow an epsilon greedy policy that's learned, then basically because these states are not distinguishable, the optimal policy will either be an epsilon greedy recommendation to go left or an epsilon greedy recommendation to go right. But because of this, I'm sorry, I shouldn't say to go right, I should say to take action R. But because action R here actually makes you go left, the problem is if you almost always execute the R action, then if you're over here somewhere, you're always just going to be looping here. You'll take the R action, take you to S, then you'll take the R action, it'll take you here, then you'll take the R action, you get the idea. Whereas if you always try to go left, it's not so good either, because if you're here, you'll just keep bumping into the wall and not getting anywhere. So a deterministic policy has this problem. And of course, the idea of epsilon greedy policies is to add some randomness into the actions so that eventually you will escape this otherwise unending banging your head against the wall or looping. But even with an epsilon greedy left or an epsilon greedy R, you don't do as well as if you have an stochastic policy that simply goes L half the time and R half the time. And so this is a nice example that illustrates, I guess it's not quite half the time, that would be here. So it's closer to 0.6 of the time. You'll go R and 0.4 of the time L. But the point is that you can easily see why it would be much better to have a probabilistic policy here, where the probabilities of L and R are much more similar than the almost deterministic policy that we'll get if we use a value function. Okay? Because the randomness will let you sometimes choose an L instead of an R when you're here and so forth. Okay, and this is in fact the value of the starting state under the learned policy in the case that we have an optimal stochastic policy versus an optimal epsilon greedy L and epsilon greedy R. Okay? All right, so that's just by way of making it as clear as we can that stochastic policies can be useful. Okay, now that we're committed to learning policies, maybe even probabilistic policies, the very first question is, well, suppose we want to represent this policy by a neural net or some other function approximator, then what should be our training objective function? What should we be optimizing when we train that neural net? And in other words, we're learning parameters theta to define this policy. What does it mean to be the best policy? What are we going to say? And if we're going to train a neural net, then we need some objective function to train that on. And it turns out, if you think it through, in episodic environments, that means environments where we have an absorbing goal state that ends the episode. And to make it as simple as possible, if you always begin in the same start state, S1, then optimizing this quantity, defining theta so that we have a policy pi theta where the value of that initial state is as high as possible, is what we want to do, right? We want to maximize the expected discounted future reward, and that's what V of S is telling us. The value of V for pi theta in that state is simply the expected discounted future reward under the policy pi theta. And so we want to pick a theta that maximizes this quantity. If we're not always born in the same start state, then we could take a sample of take the mean of this over the different start states that we're actually born in. If in fact we know a prior probability on the birth states, then we could even just get the expected value of this quantity under that distribution of states, and it would be the right thing to do. Okay, so that's pretty straightforward. The next question then, before we go on, and we're going to start with this example of a single episodic environment. But before we leave this question, if instead of having a episodic state, we have no absorbing goal state, you just live forever, and still you want to maximize your reward, then a good thing, a reasonable thing to do, which guarantees that we learn the optimal policy, is to pick the theta that maximizes instead this quantity. So what is this? It's just the sum over all the possible states of the probability of being in that state times its value function. So it's the expected value of this same quantity taken over the distribution of states that will end up in. Notice, by the way, this distribution of states is also a function of theta. If you change your policy, you're going to change the distribution of states that you visit. And so this is a common objective to optimize when we have continuing, not episodic environments. And another one which will give you the same policy is to instead just maximize the average reward per time step, which is, again, the expected value over the state distribution of the reward we're going to receive if we follow the recommended policy. And so this is an expected value over states of that. This is actually an expected value over actions under the policy of the immediate reward. Okay, so this quantity is basically giving us the average reward per step. Okay. So now again, we're going to focus for the rest of this lecture on episodic case because it's easier to think through. But really all the ideas we're talking about transfer pretty directly to continuing environments. And so now that we know what the objective function j of theta is, we just saw, how are we going to optimize that? And then we have the usual available optimization algorithms that we see throughout machine learning. We can do hill climbing, genetic algorithms, evolutionary approaches, or gradient-based methods. In fact, we're going to focus here on gradient-based methods. They've been the most successful in recent times. And so in this case, our gradient methods are going to look like this. We have some set of vector of parameters theta that define our policy. We've talked about the objective we're going to try to optimize, which in our case, we agreed for episodic worlds could be just the value of the starting state. Let's maximize that. The expected discounted future reward under the policy pi theta of that start state. And so we're going to be doing gradient ascent. We want to maximize the future reward, not minimize it. And so in vector notation, that just means we're going to get the policy gradient, which looks like this. The gradient is just a vector of derivatives. So if we have a vector of parameters theta, we're going to, at each step, each update step, do a gradient ascent by first calculating the derivative of our objective with respect to each one of those n parameters that are in our vector, and then take a step in that direction. Now, how big a step? Well, that'll be determined by the learning rate alpha. So the same gradient ascent, descent that we've talked about forever. There is one kind of cool idea for computing gradients, which is sometimes overlooked. But I love this idea, and sometimes people do this. But you know, if you have any horrible function, and you don't know how to analytically compute the derivatives, you can always just wiggle the inputs and see how much the output wiggles. So for example, if we're interested in the derivative of j with respect to the kth parameter theta k, one way to find that is just to wiggle, take whatever value we have for theta k and add epsilon to it. And then see what the new value of j is. And of course, if we added epsilon to it, then this ratio, the difference between j of theta and j of theta plus epsilon, normalized by epsilon, tells us a very good estimate of the derivative. In fact, if we make epsilon smaller and smaller in the limit as epsilon approaches 0, we have the definition of the derivative. So this is just something to keep in your toolbox of tricks. You don't need it all the time, and if you're using a function approximator where you can calculate gradients in closed form, then you don't need to do this. But it's a good thing just to keep in mind if you have some crazy representation of the policy. Because this really works for arbitrary policies, even things that aren't differentiable. Then when you wiggle it, you'll just see what the change is. Okay, so now, given that we're actually going to use a closed form for the gradient, the question is, how can we compute this? And here's a key problem, if you think about it. J of theta, again, we're going to define it as just the value under the policy pi theta of the initial state, S0. And we want to pick theta to maximize that. And one problem is if you think about computing the gradient of J, which again means how much will a small change to theta sub I alter the value of J. then you notice that there are actually two very different influences of theta on what's going on. One, of course, if we change theta, then we're going to change the recommended action in every state, or at least in some states we may, or the probabilities of those actions. That's obvious. But also, as we change theta, it's going to change the distribution of states that we actually encounter. And that distribution influences, could make changes to the value function too. So you might think because of this, it's going to be a horrible thing to calculate this gradient. But it's not. It turns out there's a wonderful thing, which is that a wonderful thing called the policy gradient theorem, which tells us that actually the gradient of J with respect to theta is proportional to this quantity. And let's look at what that means. Here, mu of S is the probability distribution over states. That is, if we follow policy pi sub theta, starting, say, in the episodic case, starting in state S0, then mu tells us the relative frequencies, the probabilities that will end up in any given state at a randomly selected time. And so here we're taking, basically, this is an expected value over the states that we might encounter. Times what? Times the, actually, this is another expected value, isn't it? That's not a helpful way to think of it. This is just the sum over the actions we could take from state S of the probability of the Q value for that state times the derivative of the probability that we'll actually take that action. Okay, so it kind of makes sense. If you think, for example, the gradient, which again is just the vector version of a derivative, if this is positive for a particular theta, that means theta sub I, that means if we increase the value of that theta sub I, we're going to increase J of theta, which is the value of the, it's a good thing. It's going to get us a higher value for the initial state. And this is saying if this is positive, then what's going on here is that increasing that theta will make more probable the action A. And you could see that would be the case if, for example, if A was the highest Q value coming out of state S. So this kind of makes sense. But we can prove it. And let's. I'll go through this a little quickly because it's in the book, as you can see. And it's actually not a hard proof. But I want to go through it to convince you it's not a hard proof. And also because the steps in this proof are now are based on the kinds of mental operations that you could not do before you took a course in reinforcement learning, but it should now be second nature to you. All of these expressions that interrelate V and Q and R and their expectations. So let's take a look at it. We want to compute the gradient of J of theta, which we agree is just the value of the first state S. And so we can write that in the standard way. V of S is simply, in terms of the Q function, the sum over the possible actions. Can I write on this? Yes. The sum over the possible actions of their Q values. So it's the expected value we're going to receive by taking the next action under the distribution given by our current policy pi. Okay, and then we can take the derivative of this using standard calculus so that the derivative of a product of two things is the derivative of the first thing times the second thing plus the derivative of the second thing times the first thing. So it's just a standard calculus rule. And now at this point, we can rewrite this part, q. Of course, the q value, you know what that is. That's just the value we're going to receive in expectation if we take action A from state S. So that's the sum over outcome states and possible reward values of the probability of ending up in that state with that reward, times that reward and the value of the subsequent state. So this is just the expected value over the outcome of our action of the usual target that we use. In fact, this is the definition of Q of A, right? Okay, and so now we can again rewrite this by noticing that this final quantity is, by moving our derivative inside to ignore anything that doesn't depend on theta. Remember, our derivative, our gradient, is with respect to theta. So I could have put a little theta under here just to make it clear that we're taking the derivative with respect to theta. And so if we want the derivative of this quantity with respect to theta, obviously this is just the current probability. The thing that matters here is the value function. And this part is just a function of the world, not of the policy. So the only thing where theta is involved is here. And so now we can again rewrite this, keeping it all the same, but expanding this v of theta, because that's what we've got an expression for. This is v of theta. V sub pi theta of s. So we can use this whole expression to substitute for that, as this is. And now you see we end up with a recursive definition. And if we expand that recursion, we eventually get the sum over states, x, times the sum over k here ends up being how many steps into the future we go. Because you can see that as we start expanding this, we're expanding one step into the future, and then a second step and a third step. So we have 3 states already here, and if we unfold this further, we'll end up with k states until we hit the absorbing goal state. And so k here is really the index into the kth state after we begin. And we make that sum up to infinity, assuming that once we hit the absorbing goal state, you just stay there forever with no more reward. Okay, so basically this is telling us this is the probability that beginning in S after k steps will actually end up in state X under the policy pi. And so we want to take the expectation over this state distribution of the derivative of pi of a given x times its q value if we take a and state x. Okay, so again, intuitively, all these things should make sense to you. And this is really an exercise in flipping back and forth between our definition of v as the expected sum of future rewards, and q as our definition of the expected value of future reward if we take action A in state S, and v as a definition of the expected future discounted reward if we start in S and follow policy pi. Okay, so then to finish this off, here's where we were. We can take this quantity here, which is just the sum over steps into the future k steps into the future for k from 0 to infinity, and just call it some Greek symbol whose name I realize now I don't know. How do you pronounce that? Eta. Eta. Okay, I was going to call it n. Eta is better if you're Greek. Thank you. So eta here just means basically this is the relative frequency of different states of state S. If we follow our policy all the way through till we get absorbed in the goal state. So that, and then times this other quantity that we already had. Here we're doing a little trickiness by multiplying and dividing by the same quantity. But that's just so that we can actually match up this count of how often we're going to end up in state S by normalizing it so that it becomes actually the probability. Remember mu before we used, and we use it here again, as a symbol to indicate the state distribution entailed by policy pi theta. So basically this is, and now we have some constant times the state distribution times this. But the beauty is now you can see the gradient of J that we wanted. Actually, the gradient depends on that state distribution, just like we hinted could be a problem. But it does not depend on the gradient of the state distribution. It just depends on the state distribution. This is a wonderful thing. Why is this a wonderful thing? Who knows? The reason this is going to be wonderful is even though we have maybe a neural net representing this so we can calculate gradients of the policy if it's a neural net, we don't have an explicit representation of mu of S. We don't even necessarily know it. And so it would be really big, serious trouble if we had to calculate its gradient. But all we need to do, since this quantity is the expected value over the state S of this stuff, we can go back to our Monte Carlo sampling methods. All we need to do is sample this and do stochastic gradient descent. And that's how we're going to end up handling this. Depends on the state distribution, but we will sample the state distribution by following the policy pi. And under the normal rules of stochastic gradient descent, this will give us the magic that we need to have an algorithm. So that's why it's important that this, even though it depends on the distribution, does not depend on the derivative, the gradient of the distribution. Okay, so now it's easy. The derivative of J according to the gradient theorem is just as we wrote there. It's proportional to that. There's this constant. But we don't care about the constant because we're going to have a learning rate anyway when we do our gradient step. And as I mentioned, you can think of that first term as just the expectation over the state distribution implied by the policy pi. So that quantity is really just the expected value over states generated by following pi of this quantity. And so if we want to do gradient descent, one way we could do it is this. We just say I'm going to update on each step from t to t plus 1. I'm going to update our policy parameters by ascending this gradient by summing over, if I have an approximate, if I'm learning, sorry, this assumes we're learning both a policy with parameters theta and a Q function with parameters W. Then I could implement this by approximating the true value of Q with my function approximator and using this directly, because I can calculate that if policy pi comes from a neural net, then I'll just do backprop to calculate that. So there's a direct mapping from this policy gradient theorem to a update rule. In fact, as the book points out, this is not used very much, although as the book points out, maybe it should be. Hasn't been explored too much. Hint, project idea. But that's one thing we could do. Or we could continue and say, well, starting with the same thing, let's rework it this way. The first two lines are the same as the first two lines of the previous slide, but instead of stopping there to write our gradient descent rule, we could do this instead. We could say, this is the sum over actions A. So this is the expected value of over actions recommended by the policy of the Q value times this quantity. And you'll see this quantity is really the same as the above, except that I've multiplied by pi and I've divided by pi. And so if I do that, then you can see that this quantity I can sample by taking the actual state and the actual action that I choose with pi and the state that I'm actually in. So basically I can sample this by sampling an A instead of taking the expected value. And I still have this left over. And so if I do this, I can estimate Q of some particular state in action by just the sum of cumulative rewards I receive when I Monte Carlo sample the world. And so that leads to this more frequently used gradient update rule, which is as I go from theta t to step t plus 1, what I want to do is I want to update my parameters according to the reward, the discounted future reward I actually sampled when I did this Monte Carlo single trajectory experiment, times the gradient divided by the policy value. So that's what we get if we derive it. So this is more frequently used. In fact, it's an algorithm called reinforce. Here's the reinforce algorithm. So to put this all together, it's a very straightforward algorithm. We input a differentiable policy based on theta. That would be like a neural net that defines the theta function. I'm sorry, the pi function. I have a pi theta. I have Greek letter dyslexia. And then we input a parameter, which is just our gradient step size alpha. Initialize our parameters, and then we just run episodes. On each episode, we follow our policy pi to generate a sequence of states and actions and rewards. And then at the end of each of those episodes, we take G, which is the sample of experienced discounted future rewards at each step. And we update theta according to that rule that we just saw. Ooh, almost the rule that we just saw. The rule we just saw had a ratio here of the gradient of the policy divided by the policy. Here I wrote that instead as the gradient of the natural log of the policy. Why can you do that? Here was our gradient rule that we had before, but in fact this ratio equals the gradient of the natural log of the policy because, if you remember freshman calculus, the derivative of the log of x with respect to x is just 1 over x. And using this plus the chain rule, I guess, the derivative of well, you could expand this. The derivative of the log of pi of x is then just going to be the derivative of pi with respect to if this is with respect to theta, then this is just going to be the derivative of pi itself with respect to theta times 1 over pi, right? So this just follows directly from the fact that the derivative of the log is 1 over x. Now, usually people write the algorithm this way. Does anybody see why you might want to do that?
Is a policy usually computed like logically?
Exactly. So if we, for example, represent our learned policy by a neural network whose output layer is the softmax layer, like that very first slide where we showed the softmax function, then in fact the outputs of the network going into the softmax layer are proportional to the log of the probabilities that we're going to get out of the softmax function. So this makes for a very straightforward implementation. You can just train a neural network, put a fixed softmax function and its outputs, and then use those outputs that are going into the softmax as logs of the probabilities. And then this gradient is just something you can turn over to TensorFlow or PyTorch or your own software. Whatever backpropagation you're doing is actually computing those gradients. So this makes it a very straightforward algorithm to implement. Okay, so there's the idea. The key steps here was we're interested in learning a policy directly. So first we had to figure out what's an analytical expression for the derivative. Well, first we had to say, what is the objective that we're trying to optimize? And we agreed the answer to that in the case of episodic training is just let's pick theta that maximizes the actual value of the starting state. That's the best policy. And then we said, well, we need an analytical expression for that derivative if we're going to use backprop. The derivative of that objective with respect to theta and the gradient policy theorem gave us a generic expression, which you see we can manipulate in a couple ways to come up with algorithms. And in coming up with these algorithms, we're relying on the toolbox that we've been talking about all semester of, for example, here we're using Monte Carlo sampling of the experienced reward for a particular trajectory. And we're using that as our estimate of, let's go back and see what it's an estimate of. We're using that as our estimate of the actual Q value for in state t taking action A, t. And if we don't know that Q value, at least we can sample it by actually running forward the experiment and seeing what the sum of discounted rewards really is. And the expected value of this over the state distribution given by our policy pi is exactly this quantity. So this trick of whenever we have an expected value of something and we don't know how to compute Q, we don't yet know Q, at least we can sample it. And in this case, we're sampling it in a way where the expected value of that sample is equal to this, which means that if we collect a lot of samples and average them together, then as the number of samples grows, that mean will actually converge to this. So that's one of our toolbox tricks that we're using. Okay, so that's the reason I love covering this stuff is it's at this point in the semester just the right way of kind of thinking about pulling together these different tools that we've talked about. Learning V versus Q, learning them with bootstrapping versus Monte Carlo sampling, deriving expressions that are based on transformations that interrelate V and Q and R, and samples of those. And it gives us a very nice, easy to implement algorithm in the end. I'm going to skip that because we said it. Now, what if you actually apply this? So if we go back to our simple corridor learning problem that we talked about at the beginning, the one where we used it to convince ourselves that a stochastic policy would be a good idea. Here you can see 3 different runs of the reinforce algorithm, of this algorithm, to learn the optimal policy. And these different runs differ only by the learning rate, alpha. So each curve here is a different learning rate. But you can see that after hundreds, but not thousands of episodes in this very simple world, those algorithms are reaching some interesting policy. You can also see that the choice of learning rate matters. So if we use 2 to the minus 12th instead of 2 to the minus 14th, it's not clear that we're ever going to converge to as good a policy as we get with 2 to the minus 14th. So there is a bit of an engineering art and experimentation involved in picking these kind of learning rate hyperparameters. But it works. Okay, so theoretically, there's also the good news that I hinted at before, which is that because the expected value of the sampled rewards over pi is equal to q, then we can prove convergence toward that, especially if if we use the gradient rule that we talked about. So the good news is that. The bad news is that the variance is high. And we talked about this initially when we talked about Monte Carlo sampling, and it's the same story. It's the same reason that the variance is high. Now, we said that in kind of an informal way before. And in this case, with this algorithm, we're actually going to look at 2 ways of reducing that variance problem. One is adding a baseline, one is the actor-critic model. But let's look at the first of these, adding a baseline. So up on top is our policy gradient theorem that we proved. The idea of adding in a baseline is this. We want to make up some function b, which is a decent estimate of q. And then what we're going to learn is the difference between q and b. So we talked about this, Katerina spoke about this earlier. She talked about, I think she used the term advantage function for learning, instead of q or v directly, learn the difference. Well, there I guess we define the advantage function as the difference between the value at the current state and the value at the next state. But here we're going to do something similar. One reason the advantage function, when Katerina spoke about it, it was a good idea, is that the values of those differences vary a whole lot less than the actual values from state over different states. So the difference from state st to t plus 1 is generally, if you collect all those samples, you have a sample with a much lower variance than you have if you collect all the actual values instead of value differences. And it's the same thing here. So the idea of adding a baseline that captures the prior for S is to do that. And the question you should be asking yourself is, or me, Well, Tom, what makes you think that just arbitrarily adding in minus b of s will let us use that gradient? And the answer is it will because of this. If you think about expanding this out, then we have q times the gradient of pi, which we had on the first line, minus b of s times the gradient of pi. But the cool thing is that negative term minus the sum over actions of b times the gradient of pi actually is equal to 0. Because the policy doesn't change our initial, we just make up a b of s function. Policy doesn't change that. So it's b of s times the gradient of this, but the gradient, but this quantity, the sum over actions of the probability assigned by pi to that action is just 1. You have to choose some action. So every policy is going to recommend probabilities on actions which sum to 1. And so actually the gradient of this constant 1 is 0. So you see what I can do is I could add any constant offset, in this case b of s, that doesn't depend on theta. And my gradient update rule will be unchanged. And so when we do that, we have this gradient update rule, which is precisely the same as before, except that instead of looking at the sample discounted future rewards per episode, we're looking at that minus b of st. And if b is a good estimate of what g's are going to be, then just like the advantage function that Katerina talked about, reduce the variance in the sample of training data that we have to fit, this is going to do the same thing. So any suggestions what we should use for b of st?
Something close to the value function.
Something close to the value function, right? Because that is the definition of the value function, is the expected value of gt, right? So in fact, b equals our approximation to the value function is the usual approach people take. So we can basically say, in our case, let's use b of st is our estimate of the value function. And now this gets us into a scenario where we're learning both pi, which has parameters theta, and we're learning a value function estimate with a different set of parameters w. But if we do those simultaneously, then we can use b equals our current value function. And this does indeed reduce the variance in this. So to be precise, what's it the variance of that I'm reducing? It's the sample of target values. It's the variance in this quantity over my different training examples. The value of this quantity over different training samples is much smaller if b is a good estimate of g than in that upstairs gradient descent rule, where I'm now looking at the variance of gt itself instead of the difference between gt and what my value function tells me it probably is. And indeed, this leads to, again, a very straightforward extension to the reinforce algorithm. Again, we're computing, we're generating episodes so that we can sample g's. We're then computing these deltas, which are the difference between the observed g and our value function, which we're using as that baseline. And then we're using that difference both to update our estimate of the value function and our estimate of pi itself. Okay, so that's the idea. And in fact, this does work. Here, if we go back to our earlier experimental results, alpha equals 2 to the minus 13 was the best alpha we saw before when we had the reinforced algorithm without a baseline, converging to the optimal policy as a function of training episodes. And the green line is what we get if we instead use a baseline, which is a learned value function. So you can see in this case, it significantly improves the convergence. And I would guess that if we looked at the sample of G values that are actually gathered by the algorithms, we'd see that the variance in that sample was indeed much larger than the variance in the G minus value function values that are used to train the green line model. Okay, so again, to pop up to the top, we like the reinforced algorithm because it converges to a local optima, but we have this variance in the training data problem. And that really is a result of this Monte Carlo sampling. You can see how you have high variance. If one path gets you high reward, another path you might get you low reward, you're going to have high variance in that sample. One remedy was to add a baseline. The second is to use an actor-critic model, and we'll look at that in a second. But first, there was a question.
Okay. I was just wondering how, like, subtracting something from a random variable changes its variance, but I realize its baseline is conditioned on the state.
Exactly, yeah. Subtracting a constant won't change it. But this is a function of state. And in fact, it's not even an arbitrary function. It's our estimate of the value function, which is and the true value function is actually the expected value of G. So it's a very carefully considered baseline. Yes?
So I'm confused with the direction we're in circling. The previous slide where you had the two graphs. Now you have two hyperparameters optimized.
Yes.
And it's converging faster, right? But it's like you've got more experiments.
Well, yeah, you raise a very good point. If you look at the fine print here, this is reinforced with alpha, the learning rate, set to 2 to the minus 13. The green line, the fine print says, here alpha is 2 to the minus 9. And also alpha w, the learning rate on our value function, is a different number, 2 to the minus 6. And so I'm sure, well, I haven't talked to the authors. I'm guessing when they wrote the book and created this plot, they searched over different values of both the hyperparameters to make this plot look as good as possible. To be fair to them, though, they did use the red line there is the best of the plots from the previous experiment. So they are using an optimal, or as good as I think they've probably found, alpha for the red line as well as the green one. But yeah, there could be, whenever you do that kind of hyperparameter search, you're also opening yourself up to possible overfitting. If you reran this experiment, you might not get exactly the same optimal hyperparameters, and so it is an issue. And the more of this kind of stuff you do, the bigger that hyperparameter search can be. It makes me think, and then we're going to stop for today because I want to give Katerina a chance and pick this up next time. But it makes me think that the difficulty of doing that hyperparameter search here's a hypothesis that might be true or false. I think the more functions the next idea we're going to talk about is bootstrapping, which is the same idea that we talked about before. It's in our toolbox already, of instead of relying on G's, let's rely on Q's and V's to calculate the target value. and not even use G's. Here we're still using G. It's just our target value is G minus our approximation to its expected value. My hypothesis is the more redundancy you put in the system, as in have it learn V and also Q and also a policy, the better they're going to robustify you to errors, these kind of overfitting issues, including the ones in choosing hyperparameters. But that's just a hypothesis. Hint, project idea. Okay, so let me turn it over to Katerina, and I'll sit down for a second.
Okay, so I really like I think I haven't seen before this type of derivation for the policy gradient. The only thing I want to mention is the following. Like few slides ago, we started from this summation, mu s, the on-policy distribution over states, summation over actions, a log of the policy multiplied with the Q function. And this is where we end up a slide ago. So in the beginning we said, no, not many people use Q, so that is historically. Historically, yes, we started by using the Monte Carlo estimate instead of the function approximation for Q, right? But right now, all these actrocritic methods, they all use function approximation for Q. Now, why would we need to go to advantages versus Q? Imagine that I choose my reward to be 2 at every step and 200 till you reach the end goal, or 2 at every step or 2000 till you reach the end goal. How I choose my reward function will impact very much your Q. But if you put advantage, then you are not impacted anymore because you only care about the relative benefits of different actions, all right? So you don't have this hyperflation of your Q as someone is changing the reward function. So that is one way to think about it, but we will see also numerical examples where you'll see what happens without advantages and what happens with advantages. Advantages, I mean, you see here the baseline in the next lecture, so that's why you should not be stressed out, or I really didn't get it, because the whole next lecture is what approximation should we use with Q, how should we estimate the baselines, how we should estimate the advantage functions. Each tiny little variant has its own name and its own paper and comparisons, so, but they're all extremely, extremely similar. Yes, so this is the whole thing we're going to talk about in the next lecture, so you should not worry about this all to be disentangled right now. Interestingly, historically, yes, although this beautiful formula shows Q, we were using Monte Carlo returns where somebody could say, you know, straight away we can start with using the function approximation for the Q value there, right? The same as this formula was suggesting for the policy gradient theory. That's it. See you on Wednesday for continuation on those.